Hello, everybody. Welcome, welcome. Thank you, everybody, for coming. We're going to get started in just a minute here. Do a quick intro. My name is John. I'm with Arize. You guys will hear from me a little more later. I want to say a quick thank you to the GitHub team and the GitHub staff for hosting us here. We're really excited to have everybody. So one big thank you for the GitHub staff, first off. Thank you. We have about 4 speakers for you guys today. We're going to go through all different topics all around agents. So we have everything from evaluating agents, Agentic RAG, multi-agent systems, a lot of fun topics for you today. And yeah, I guess without too much further ado, we're going to kick it off with our first speaker, who is Arize from CrewAI. So please welcome Arize.
How's everyone doing? Good, good? Sweet. All right, everyone, my name is Arize. I'm a software engineer at CrewAI. But before I begin my talk, I just want everybody to think of something that they do every single day, something repetitive, maybe even mind-numbing. Don't we ever want to think that we could just delegate those tasks to somebody, like an intern or maybe something? Well, today I'm going to show you guys how do you automate the boring with CrewAI. So I'm sure everybody here knows what AI agents are. To those who don't know, AI agents take this high-level goal, like analyze market trends of my competitors, research the latest news about AI, create a marketing campaign for my product, or even find the best talent for my job posting. It takes this high-level directive, and an AI agent using tools will execute and plan all the steps it needs to generate an end output fully autonomously. So, what is CrewAI? CrewAI is the leading open-source multi-agent framework, and we make building agents so damn easy. Your agent just needs a couple things: a role, a goal, and a backstory, and some tools. Then an agent has a task that it needs to execute, like here's a description, an expected output, and then the agent that you want to execute this task. Combine all of those together, you get a crew. Your crew has agents, a bunch of tasks, and a process. So what's the anatomy of a crew inside CrewAI? Each agent has the ability to cache and use memory. They have the ability to be trained using reinforcement learning with human feedback. They have guardrails like executing code in a Docker container. They can use tools, obviously. And they do cooperation through role-playing, delegating tasks to one another, agents delegating and asking questions to one another, just like a team does. We have different processes that you could use to run your crew. We have a sequential process that has one agent running one task, sequentially, one at a time. We have a hierarchical approach where you have a manager agent delegating tasks to specialized agents for that particular task. You could even run crews in parallel. So say you have n number of inputs, can you run these crews, making like an entire automation, essentially. And you could even run tasks asynchronously, so they're not blocking one another, speeding up the process of your crews. So for an example, what we're going to do is build a financial report generator. It's going to extract relevant documents from a knowledge base. We're going to use a coding agent to generate Python code to generate graphs that you see over here on the right. And then we're going to take all of those things together and generate a report. This is something a lot of associate level people do every single day. So how do you get started? Just do pip install CrewAI tools, and then with our CLI command, do CrewAI create crew, and then the project name. But that's for developers. But even without developers, you could do this with our CrewAI Enterprise Studio. So take this high-level goal, like build a financial report crew that extracts data from a knowledge base, then generate the charts based off a user query, then using the financial data extracted, create a report for our stakeholders that could be presented for our financial data and trends meeting. And then our studio will scaffold all the agents, all the tasks you need. So you get like 80% of the way there, and this is pretty much your building blocks for building agents without having to touch a single line of code. But if you do want to code, there is a button called Download Code over here where you could begin to enrich your crews. So building agents is super easy. with a YAML format, you could define agents. We have 3 agents here. We have our first RAG agent, and we have our graph generation agent, which will generate Python code to pretty much build those graphs. And then we have a report for stakeholders agent that will take all of the financial data that we extract from our knowledge base using the Weaviate tool, which I'll show you how to build, and then generate a report. Then again, we have our tasks. So we have a task YAML that you can define all your tasks. Your task just has a description, an expected output, and then the agent that you want to define. And then we have the ways of building custom tools, right? So we want to extract knowledge. We want to do some RAG over knowledge base. So I've uploaded documents or financial docs from 2020 to 2024. This is like mock data. Extract this from Weaviate, and then you can see over here, financial docs.generate near text, finding something semantically similar to our user's query. And then we could attach that to our agent. So our RAG agent now has a tool called the Weaviate tool that it can extract relevant documents based off that given query. And then now we want our second agent, the graph generation agent, to execute code. This can execute code in a Docker container, again, with guardrails, so it's not like deleting files, things of that nature. And all you have to do is enable the flag, allow code execution. And then this is how you run it. So our inputs is generate a report of net income and gross profit margin for the business for years 2020 to 2024. We could kick it off, and this is something that we get. So we get a cool graph, and we get a quarterly report that our stakeholders can now use. But this lives on your local device. This is something a non-developer can use. Like if they don't know Python, how are you going to be able to use something like this? So you could deploy your crews now. You could push your crew to GitHub, sign up using app.crewai.com, and then start deploying your crew. You could do this. You could start for free. So again, we have the RAG report generation example. We pass in our environment variables, and we can get started. So most engineers and project managers use tools like a Kanban board, like Linear, Trello. So why can't your AI agents do the same or live in the same place to be managed? You have a backlog of items that are waiting to be executed. You have things that are running once they're being executed, and then you can finally see end results, right? How many tokens did this cost? How many of them were prompt tokens or completion tokens? How many of the requests were successfully executed, and how much did this cost altogether? Then now you could start extracting all of your documents, all of your expected outputs directly from our Kanban board. Then we have a layer of like observability. How many tokens did this cost? How much did it cost? What did your agent do? And what were their expected outputs? What tool did they use? Furthermore, how do you iterate? How do you stay in the platform and continue to test and monitor your crew executions? We use LLM as a judge to evaluate your outputs to the expected outputs that you've defined. Additionally, we have a way to determine faithfulness depending on how the context provided, did you use the right details? Like for example, here, the data points for net income are consistent with the reference text, right? So are you hallucinating facts, or are you taking facts that were passed from the Weaviate tool or tools that were delegated from one agent to another? So I mentioned reinforcement learning with human feedback earlier. You could also do that directly on the platform. So you could train your agents, you could provide suggestions as to how you can improve these outputs, right? Like you need to use the Weaviate tool with a certain kind of query, or use XYZ things to kind of better improve them. So after every next execution, your agents get knowledge or insights as to how to execute better. And then finally, we have a way to kind of have a global scope of all the things your crews have been doing. So how much was the average prompt tokens? What was the average execution times? How much did this cost? And monitor that over time. Then lastly, we have a way of visualizing your tools. So how many times did you use the Weaviate tool? How many times were the code interpreter tools being run, all in one place? So just the last thing to wrap up, what should you build? There's a lot of cool things that you can try. So just like I started, think of something that you do every single day. Maybe it's for yourself or people on your team. Maybe try to use AI agents to automate that. Just to wrap up, you can join our community.crewai.com if you have any questions. Our forum is probably the best place to ask questions and receive help from our staff like myself or other people in our community. But that's it for me. If you guys have any questions, I'll be here for the rest of the night. Thanks. The question was, what is the difference between CrewAI flow versus the orchestration? So flow enables regular Python code to be chained or in addition to regular crews. So you don't need crew being executed on flows. You could attach your agent in task level, just executing that, then appending like regular Python code right after. So you have a little bit more control. And the regular orchestration is like, think of having like a full self-driving car. All of your agents being executed are just being handled by the agents themselves versus having to include regular Python code in between them. Does that answer your question? It depends on your use case, but we could talk about it if you have a particular use case after this. I think that's a great kind of use case when it comes to multi-agent applications, right? You have particular use cases that certain models can be a little bit better at, right? For example, if you have a coding-related task, maybe you want to use a higher frontier model like Claude Sonnet or GPT-4o as an example, but then you want something to generate reports where you don't need the best of models. You could use something like a GPT-4o mini, saving you so much money. So at scale, you could see the differences between 1 million tokens for GPT-4o being like $1 versus GPT-4o mini being like 15 cents, right? There's a bit of a stark difference between choosing what model for a specialized agent and a particular specific task that it's executing. Yeah, so I think the question, what I've heard is, if the first agent hallucinates, that probably has a cascading effect of your other agents also hallucinating, right? So how do you kind of guardrail against this? We have tools built into our platform that give you this insight as to hallucination results, so you could easily start to iterate and then use our training feature. There's also other companies like Arize where you could have observability across all traces and like multiple levels. So we're actually, I think, have an integration with Arize and other observability companies. So I think the next talk will actually give you a little bit more insights as to how you can do that. But again, on our platform directly, you have the ability to test and then iterate with train and then kick off new executions with added context to prevent hallucinations. Yeah, if anyone else has other questions, I'll be around, so.
Hello again, everybody. Thank you for that awesome setup into the talk about evaluation. Okay. Give it 1 sec to show up. Awesome. All right. Cool. So, as I said before, I'm John. I'm a developer advocate at Arize. I'm going to talk to you guys for the next 10 minutes or so about evaluating agents and assistants, so the tools and techniques that we use to evaluate assistants and agents. And we'll save some time for questions at the end of that as well, too. It's a little more like theoretical. Like I'm going to go through the theory of how to do this. I'll talk a little bit about Arize and what we do, but I'm going to save that for later if anyone wants to follow up afterwards. So just a quick show of hands before this event, who had heard of Arize or used Arize before? I love that there's more people every time I ask that question. It's really a nice feeling. More people are hearing about us, so that's great. So one of the kind of core theses we have at Arize is that one of the reasons that there's not more agents and AI applications in production is that observability, or is that these applications haven't quite been able to build confidence in the responses from the agents and from the models themselves. So having a tool for observability, like the ones that we put forward, is kind of how we think about addressing that particular problem. So there's a series of issues that we see people facing when they're building agents, applications built on top of LLMs. That manifests early on as lack of visibility into what's happening inside of the application. So not being able to see with the different calls that are made. If you have an agent, not being able to see the different tool calls or the responses from those. So having that visibility early on becomes one of the main problems. And then as you start getting further into your application development, becomes more about evaluating the effects of making different changes. So if you change a prompt, if you change a model, if you change something, what downstream effect does that have later on? And how do you make sure that you're not breaking different parts of your application by making these sorts of changes? And then as you get into production, it becomes more an issue of preventing either really acute bad performance issues, protecting against jailbreaks, PII leaks, a bunch of different kind of areas like that. And there are the kind of acute versions of mess ups here where you see situations where agents are recommending someone puts glue on a pizza to improve the tackiness, or selling a Chevy Tahoe for $1, or giving people a bunch of discounts when the discounts don't exist. So you have kind of the acute issues of, or the acute consequences of not having proper evaluation techniques in place. But you also have the more mundane stuff, which is just your model responding, I don't know. It's hallucinating in a more minor, kind of mundane way that can't respond to certain questions that it should be able to respond to. And so we're trying to kind of address all of these different pieces with Arize. So everything from tracing, evaluation, experimentation, guardrails. And then we've actually done something cool where we've built our own Copilot agent into our platform that can help you debug the platform and debug your traces and your spans and things like that. So a lot of the learnings that we've had about how to structure agents and evaluate agents and kind of create these different agents partly comes from the Copilot agent that we ourselves built into the platform. So there's kind of a Ouroboros situation here where we're using our own tools to evaluate the agent we built to work with our tools, which is fun, but that's where some of our learnings come from. Cool. So with that, I'm gonna kind of switch gears, focus a little bit more on the how do you evaluate agents, how do you structure these, how do you evaluate both agents and multi-agent systems. So it's useful to kind of start with what we see in the ecosystem for typical agent structures. I think a lot of people in the room probably are familiar with agent architectures and how agents are built, but just as a really quick kind of outline of what we see, because there is some variation there, the typical kind of structure we see for agents involves some sort of routing or planning step. So when you have a user input, goes into some sort of router or planner to decide between calling a bunch of different either skills or functions or kind of tools that that agent has access to. And then after you actually complete that tool, you may have the agent go back and do another cycle through that. It might go back to its router. It might do some more planning from there and kind of continue on. It's a little bit of a simplification here, but this is kind of the typical structure that we see a lot of agents being built in. And so you can end up in this kind of looping structure where you have routers going to skills, then back to either user input or back to that same router and kind of continually looping through. And very basic example here, you guys have probably seen some of these before, where we have maybe an OpenAI or some other kind of model acting as the function kind of routing step there. So taking a user input and routing that input into some given skill. You might have like a chat to purchase app or agent that would go on a site, and you could call different skills for item search and then for kind of Q&A, general Q&A. So very basic structure that you have here. You can imagine, though, that this gets blown up and this gets a little bit more complicated as you actually start talking about production, real enterprise agents. And so this is I won't tell you who, but this is a real agent that's out in the world that is kind of built and is working. It is a similar kind of like chat to purchase agent that exists on a website. So it's an agent that's receiving some different kinds of user inputs and then can call one of these different skills. It's product comparison, product search, et cetera. And then those branches might themselves have other LLM calls. They might have API calls they make. They might have other code that they run. And so you can imagine as you're trying to evaluate this structure, there's a lot you could evaluate within this, and it can get very complicated to structure that and figure out, okay, what am I evaluating? How am I evaluating it? How does that all work? And so I'm going to dive into a little bit of kind of the how you evaluate agents. We're actually going to start with the what you evaluate within an agent, and then we're going to go into the how you evaluate this. A little bit of info on the difficulties of evaluating agents. I think this is somewhat self-explanatory. We're going to kind of keep going to make sure we can get to everything. So let's start with the what. So when you're evaluating an agent, what are the different pieces of the agent that you should think about evaluating? The first is the router, which makes sense. And again, not every agent's going to have a function calling router. You might have some other kind of system that's choosing which path to go down or which kind of skill to call. but you still want to evaluate whether it's making the right choice, how it's structuring that call. So the router is going to be the first piece that we evaluate. The next is going to be the individual skills or functions that it goes down. So if you have a RAG skill, if you have even an API call that's going to get made, you will usually have some sort of evaluation on whether that's being sort of completed correctly. And then the last piece that we'll evaluate is the path. So is the agent taking the right path through its different skills? Is it looping in perpetuity? Is it actually kind of completing with some sort of efficacy here? Within the router, there's a few more things that you could actually evaluate. So one is the obvious choice of, is it selecting the right skill? Is it selecting the right function to call? And then the second piece of that comes up, and it's actually the more difficult one we often find, is it extracting the right parameters from the user query to fill in that particular call? So is it pulling the right parameters out? Is it passing them into whatever function it's generating properly? If you have a user asking, what's the status of my order 1234, it has to know that that's an order ID and not a shipping ID or some other kind of ID. So are you extracting the parameters correctly? Oftentimes is the harder thing for models to get right if you're using a function calling approach. So we have a couple things we can evaluate within the router. You can evaluate function generation, but I would honestly say that that is done properly in almost every case we see. So I think skills and parameter extraction is the easier place to focus. And then there's this idea of converging. Are you making progress with your agent as it's moving through different steps? I think transparently, this is the piece that there isn't really a one-size-fits-all method to kind of evaluate this idea of convergence. Is your agent converging on an answer? So this tends to be done with more, there's some interesting ideas around kind of identifying problematic nodes in the graph as they're executing and going through those different pieces. But oftentimes in practice, we just see people measuring the number of steps that the agent takes, and then you look for similar queries that the agent receives. Are there outliers in the number of steps that it takes to answer that query on certain times versus others? And that can be often a pretty good starting point. We have people joke that the vibe test is like the test for convergence, and it's more complicated than that, but there is a kind of immediate version you can go to that goes one step above that. Okay. And the last piece about the kind of what we're evaluating and the kind of structure around it is it's all well and good to set up these evaluations and set up these evaluators, but to actually then use this in production and use this to help you kind of improve your application, you need to have a structure around how you tackle these. And so this is where this idea of evaluation-driven development comes into play. So the idea here is that you set up a set of test cases or a data set of test cases, and then every time you make a change to your agent or your multi-agent system, whatever it might be, then you run all those inputs through your agent, take the outputs, run them through a consistent set of evaluators, and then that gives you a comparable kind of set of data that you can use to measure performance improvements in your agent over time, and also make sure you're not breaking things in a different part of your application. All right, so that's kind of the what and the structure. In terms of the how, let me take a quick poll again one more time. Who is familiar enough with LLM as a judge that they could explain it and kind of go into detail? Who's built stuff with LLM as a judge before? Anybody? Okay, few people. Okay, cool. We'll go through that quickly because I don't want to spend a ton of time going through it if everybody knows it already, but it sounds like some people are newer to the concept, so that's great. In terms of how you can run these evaluations, Lorenz got into a little bit of some of the ideas around comparing to ground truth or using an LLM as a judge evaluator. Those are kind of the two main categories that we see of types of evaluations, of techniques you can use to evaluate things like the router in your agent. So the first being ground truth evals. I won't go through everything in here, but happy to answer more questions about it if people are curious. But your ground truth evals are generally where you're comparing to some sort of ground truth. So if you have a bunch of test cases, you know what the expected output is of those test cases, and then you can compare your agent's output to the expected output in some sort of way. So maybe you're doing a similarity comparison, maybe you're doing more like computed kind of KL divergence of the distribution of those outputs. There's a lot of different kind of metrics you can calculate to measure the difference there. But this is where things like your precision and recall scores and F1 scores can come into play. And this is always going to be a part of whatever kind of evaluation system that you want to set up. You always need to have some sort of comparison against ground truth. But that doesn't really give you everything that you need. It's hard to actually come up with ground truth comparisons for every kind of evaluation. It works well for things like skill choice or parameter extraction, but for things like hallucination detection, it's much harder to do. And so this is where LLM as a judge can come into play. One of the very nice things about LLM as a judge is you don't really need ground truth to get started with it. It's helpful to tune your models later on, but you can get started without any kind of ground truth. And you can also measure things that are more subjective, like hallucinations or relevancy or something along those lines. The way that LLM as a judge works is, as the name sounds, you're using a separate LLM to kind of make the judgment about one particular axis within your model. So if you had a case where your model had some sort of RAG pipeline in it, you could take basically the query, the context, and the response, gather all those up after it's run, send them off to another LLM and say, hey, separate LLM, is anything in this answer hallucinated based on the question and the context that were added there? And then that separate LLM says yes or no. So this is a tool you can use to kind of set up these more, we'll say, more subjective evaluations or qualitative evaluations. And to give a little bit more detail, this is kind of the same chart we just looked at, just gives a little bit more detail about what that looks like. But one thing to call out is this template on the bottom left for you guys, is kind of the template that we would use to actually detect something like, I think in this case, it's relevancy that we're looking at here. But you could structure that template to really be whatever you wanted. So it does allow you to do more of a broad range of evaluations that you can use to evaluate some of that stuff within your agent that we talked about. Like even the convergence can be done in this way a little bit. One thing that we have within Arize that's very helpful with LLM as a judge too is that you can actually generate explanations of why certain labels were chosen. So you can have it generate, okay, this is the piece that was hallucinated, this was the incorrect call that the agent made in choosing a next step, and so you can easily see at a glance, okay, what was the error that was made and how can I use that to then go and debug from there. I can come back to this if people want. I know one of the questions I always get with LLM as a judge whenever we talk about it is, how do you avoid situations where the judge LLM hallucinates, or how do you avoid situations where you're just kind of compounding these sorts of issues? One of the ways that you do this is just by using a very large model, but happy to dive into more of the mitigation strategies if people are curious. And the last piece I have here is just a little video I'll leave on loop that's showing some of this in our platform. This is showing our Phoenix open source platform, but we've essentially added evaluation labels for function calling and parameter extraction to individual runs of an agent. You can see the explanations that are being added within there as well. And so you can see this is one of the nice things. It's easy to understand why was the incorrect label added there, why was that not a correct label. And then from here, after you've identified those things, you can create data sets out of them, use that to test changes to your prompt or your agent as you continue forward to see if you're actually improving your execution over time, or if you're just kind of making changes that don't have some big effect from there. So we'll let that run in the background here. That is the bulk of what I had prepared for you guys, but happy to take any kind of questions either around agent evaluation, LLM as a judge, any of the techniques or anything that we talked about there. So any questions? Oh, yeah.
Is it possible that the LLM as a judge hallucinates the same thing that the original LLM hallucinated?
So yes and no. I think yes, the LLM as a judge could hallucinate in some way. Typically, the way that you structure these setups for the templates, though, is you're having it respond with like a very specific label. So either hallucinated or factual, incorrect or correct, or something like that. And at least within our platform, but there's other ways to do this as well too, we will actually like snap the response of the model to one of those labels. So it's possible that it just gives the wrong label, but it's like sort of it's not a hallucination in the same way that it would just like make up something different, but it could get it wrong, for example. And so that is a good caveat with LLM as a judge. It's not going to be 100% correct all of the time. You can get to very high alignment with human labels, but it's never like 100% correct. So there's techniques you can do to kind of tune your prompt that you're actually using here to kind of align that more appropriately, testing different models as your judge model. There's a whole kind of area in there of how you close that gap, but it can hallucinate in some way. So you can have it be a scoring task, but one thing we found is that models are really bad at continuous scores. So if you say like score this from 0 to 100 on how good it is, well, most models don't know what like a 63 versus a 67 versus a 74 is. And so you don't get a lot of consistency in the scoring, because also each case tends to be a discrete thing. It's not like it knows previous cases. You could feed those in, I guess, and to add more consistency, but it gets a little bit more complicated in that way. You can do things though, like say score it from 1 to 5. 1 is this, 2 is this, 3 is this, 4 is this, 5 is this. That will work as well too. So it's hard to get away from a classification task for it, but you can broaden the number if you want to. Yeah.
Can you repeat the question, please?
Yeah, sorry about that. The question for that last one was, would you ever use an LLM as a judge, not as a binary classifier, but more as kind of just a general response that you could get? Yeah. I'll do one more, and then we should probably get out of here.
If my chatbot takes human feedback, can I use that human feedback along with the data to write that LLM as a judge?
Yeah, so the question was, if I have an app or a chatbot that takes human feedback, can I use that human feedback to write an LLM as a judge setup? Is that right? Yeah. So yes, you definitely can. That's one of the good ways that you can actually structure and tune an LLM as a judge, is you get some set of ground truth data, which could be human feedback in that case, and then you can use that to either tune your prompt. You could even fine tune a model to use as an LLM judge if you wanted to go to that extreme. I think usually we see people tuning prompts and kind of testing different prompt iterations against that ground truth set of data from human feedback. So great question. Cool. I will be around here for the rest of the night, so happy to take other questions that people have. Sorry, we want to keep us going on time here. Please join me in welcoming our next speaker, Ofer from Vectara.
Thanks, John. All right. Hey, everyone. I'm Ofer, Head of Developer Relations from Vectara. And I'm going to show you today how to build Agentic RAG applications with Vectara really quickly. But I'm going to start with this. If raise of hands, who has ever seen an episode of Knight Rider? Okay, quite a few, actually. This is probably in the 80s, if I remember correctly. David Hasselhoff was this PI detective who saved the world. And he had this car called Kit, which was really cute in the 80s. It could drive on its own, self-driving car. And it could also talk and help him. So I think I'm showing you this to say, we're not quite there. I think, the self-driving car is almost there. Waymo is doing pretty good, I think, some others. The thinking on its own agentic capability, I think we still have to work a little bit at. But I wanted to share with you quickly, we got there pretty recently, right? So there's two things, I think, that have happened in the last maybe, let's call it 6 to 9 months, that have made this possible. One is called tool calling. I'm sure you heard of those, and agent reasoning and planning that have just matured enough to where agent starts to be working really well. Tool calling is the idea that, of course, the LLM doesn't respond with just text. It responds with kind of a tool call or a set of tool calls, and you actually execute those tools in whatever agentic framework you have, and then respond back. And so it can actually, be having these superpowers with the tools. And then agentic reasoning and planning, and this is an example of something called React, but there's a couple other versions of this where the agent, the LLM, essentially kind of gets a user query and plans how to execute and get the response back based on the tools that it's provided. So this kind of looks like this. There's a lot of different ways to look at this, but generally you have the agent kind of doing reasoning, understanding the intent, planning, given a bunch of tools that you give it, and calling these tools. And these tools could be a call to a RAG query, but they could also be a call to like an API you have in your company, or maybe even a database SQL query or some custom function that you write in Python. And then it collects all this information and crafts the response to back to the user. So it's very powerful. We're sort of giving the LLM superpowers. So as I mentioned, again, tools could be a lot of different things. Essentially, it's usually any Python function you want, but you can do stuff like call APIs, call databases. And then in some cases, people go to actually taking actions. And I would argue, for the most use cases, I'm not very comfortable with that. I think there's still hallucinations I'll talk about next, but taking actions is more dangerous. So let's say I want to book a flight, and I ask the agent to book a flight to Paris, and it goes to Tokyo. So that's not going to be very good. So I got to be careful with that. I think the action part is still a little bit difficult. With a lot of work, you may be able to make it work, but I think getting the low-risk actions of getting stuff that you can kind of get a response and still kind of as a user evaluate the quality of that is safer in this case. And Let me give you an example, right? I wanted to write an actual example even, of why hallucinations still matter, even matter more in the world of agents, right? So this is my example. I think there was a question earlier about multiple agent compounding hallucinations right over here. This is even within the same agent when you have different tools, and one tool says, who's the JP Morgan CEO? And it's not Jane Fraser, that's Citibank CEO. So you make that mistake, and then tool 2 will then say, what did Jane Fraser say in this conference? And of course, she wasn't there, so we'll say, I don't know. So you get this error at the end of the flow, and you can imagine this becoming 5 steps or 7 steps, and you can go like wild. And of course, when you take action after that, you can run into a lot of problems. So I want to talk a little bit about hallucinations more. It's actually an area that at Vectara we tackle quite a bit, and we work quite a bit on reducing hallucinations. And this is one of my favorite slides of why do LLMs actually hallucinate. There's a lot of different reasons, a lot of different ways to explain it. This is one angle that may not have shared broadly enough on the internet, or I haven't seen it that many times, so I wanted to share it here. LLMs generally are kind of, you can think of them as compression algorithms, compression systems. They take all the knowledge they've been trained on, which usually is trillions or hundreds of trillions of tokens and data from the web, and they compress it to a model that's usually, billions of parameters, maybe 100 billion parameters, something like this. So there's definitely like a 100x or even 1,000x sometimes compression there happening. And we know that lossy compression starts at about 8x compression ratio. So you can keep the lossless nature of compression out about, for normal English up to about 8x. So clearly you're losing some information. And that's one of the reasons, or one of the explanations why, sometimes the model doesn't know what's next and just starts hallucinating instead. It's a little bit like, in college, or we don't go to 4 years of college to learn and memorize everything we've been taught in every class. We just want to learn the concepts and the ideas and the generalizations that we can apply in the techniques. And that's similar to this compression. That's the same idea. All right, so one thing that might be interesting here is we've developed something called the Vectara Hallucination Detection Model. It's part of the Vectara platform. If you use it, it comes back with every query. But we also have an open source version of this. It is a little bit weakened. It's English only, but it's still very valuable for the community. And it's available on Hugging Face here. You can see this, and you can download it and use it. We also have a leaderboard you see here that shows that we measure different LLMs and their kind of propensity to hallucinate. So this is really helpful because if you take a look at it, it may be surprising. Some of the models you thought are pretty good may not be as good when you look at that metric. It's a very popular model on Hugging Face. It's much more than 2 million now. I think it's close to 3 million almost downloads since about a year ago. So it's very popular and very useful. And John mentioned earlier the idea of faithfulness as a metric. So think of this as kind of similar to faithfulness. So it measures the likelihood of, not the likelihood, but is a generated summary kind of hallucinated given the context, given the facts that you get in RAG. And it is a model that's, I forget who asked the question, but it's a 0 to 1 metric. It's just a model. It's not using an LLM underneath. So that has a lot of benefits. One of them is that it doesn't cost you LLM tokens. It doesn't add extra latency. It's also a pure classifier, so it's kind of a 0 to 1 sort of number, which you can use however you like. So, I think it was mentioned too, like LLM sometimes change their minds on LLM as a judge, but they're random. This is just a pure kind of predictive model that's pretty stable. So it's really cool. Okay, so back to creating agent in minutes. So we've created this package called Vectara Agentic. It's open source and it helps you create agentic applications with Vectara. You can check it out on PyPy. Also, the open source version is on our repository, and we have some documentation. And before I jump to show you how to build with it, I just want to give a shout out to Arize. Again, we integrate with them for observability of the agentic framework. So you all know what Arize Phoenix is. And this is very simply how you configure Arize to work with Vectara Agentic. You just set up the observer type as Arize Phoenix, and if you want to use the the Arize service, you can set up your key and everything. Otherwise, you get a local sort of view of this, like a local installation. And one of the nice things about the integration is that you can get in the Arize observability results. You can see here it's called FCS. That's the factual consistency score, which is the kind of commercial version of HHEM. So you get that back from our system, and it kind of shows up in the query as well. You can see what happened there and was something hallucinated or not, etc. Okay, so I want to show you one cool demo with Vectara Agentic. We have a couple on Hugging Face you can look at later. But this one I like to show because I think it's really cool. So it's a simple application. We took two data sets, one on electrical vehicle information, so a bunch of websites that had information about types of vehicles and things like this. The other one was about laws and regulations of electric vehicles. Again, both of these are ingested into Vectara. We build them to be a query tool, and we give it to the agent as tools, essentially. And the third one is we picked up a bunch of data that is structured data, so a bunch of CSV files, essentially. We put them into a database. So you can actually query them using kind of database tools. The agent doesn't know what's in the data. It just has a description. So the way you build the agent is you sort of give it a bunch of instructions, like I'm a research assistant with expertise in EVs, and you give it the tools that it has. And let's see what it looks like. So if I go here, sorry, why is this small? All right, so I'm going to show you one example here, and you can test it out later. But this is a question that shows both a kind of a textual query as well as a kind of query on the structured data. So I'm asking the types of, the difference between BEVs and PHEVs, and how many were registered in the state of Washington in the past few years. And as you can see, it gives you this part, but also the structured query part. And what I wanted to really show you is, what I get excited about is this, right? So let's see what happened underneath the covers here. It decided to first call this tool, which calls Vectara underneath and gives you the textual part based on the EV laws and EV regulations piece. So that's pretty straightforward. It gets the right response. No issues there. And then remember, it doesn't know what's in the data. It just knows it has a database with some tools. So we gave it these tools. So first of all, you can list the tables. So say, okay, here's the different tables. And then it decided to call this thing called describe table with this table because it knew it was about registrations. And what this does is it gives you the schema of the table. And then there's a tool called load unique values. So it knows that it needs to understand not just the table schema, but the value structure. So for example, Tesla could be uppercase or lowercase or all kinds of cases. So if the tool doesn't know, if the agent doesn't know how it's structured, it may run a wrong kind of SQL query. So it asked a bunch of questions about unique values. I got the actual unique values exactly how they're used here. And then this is the cool part. It actually created its own select query at the end to really compute the information it needed, got that response, and send it back to the agent to display for us in this beautiful form. So that's the agent. As I said, really, really cool to build it out like this. And then that's all I had. Thank you very much. Thank you. I'll take some questions. We have some information here if you want to try out Vectara, sign up, our documentation. We have a Discord server. If you like Vectara Agentic and use it, would appreciate some stars on the GitHub. And also, we have some shirts over here for you as well. But let me see if we have, John, do we have any? Thank you, John. Do we have any time for questions? Yeah, we have a couple minutes. All right. Yes, over here. So the only thing I gave it, I'll show you here in the, I think it's in the screenshot. The only thing we gave it is this database tool. So we said here is, it's called, we have a prefix if you have multiple databases, and then the content description and how to connect to this database. And that's it. And all these tools that get generated that allow it to query the database in different forms. Yeah.
So to follow up on that, because if you have different sources, like databases, like you're looking at BigQuery, you're looking at something in Azure, like how is it gonna? That's what I'm curious.
So the question was, how do you connect to these different databases?
How do you program an agent for those queries to make sure that it gets that syntax?
In terms of SQL syntax?
Whatever database you're using.
Yeah, so I haven't tried it on all the different database types in the world, but generally I think if you use standard SQL, this should work pretty well. I think, again, you can always give the agent special instructions and say, this database is actually, remember we have these instructions here, so you can give it instructions to further qualify to say, hey, this is a particular brand of SQL and use it this way or something like this. So agents are very good when you find an issue that doesn't work and you kind of give them special instructions. Yes. Over here.
I wonder if there is a chance that we can kind of get part of those databases to it, so we can make it faster, in the way that, it gives us answers in real time, for some application that needs it real time, not so much, so much loop and searching and this stuff.
Great question. So just to repeat the question, I think it was, how do we make agents faster and respond in real time, right? So it's a great question. Look, LLMs are still pretty slow. I worked in LLMs, by the way, since 2019, when GPT just turned 2. And the models weren't that big, and they weren't very good, but they were actually quite faster because of that. So it was like 170 million parameters kind of thing. Today, they're pretty slow. They used to be much slower. So if you use GPT 3.4 at the early days, it could be 20, 30 seconds for a response, right? Now with GPT 4.0, it's usually like 3 or 4 seconds. But still, if you have multiple calls, you might kind of accumulate that time. So a couple of these planning algorithms I mentioned, like React, there's others that work with parallelism that make it faster. So they call tools in parallel when they can. So that helps a lot. And I think the industry as a whole, I think we'll see in the next couple of years a lot of improvements in inference time with just better chips, better algorithms, better approaches. If we also have a guest on our podcast, if you're interested, called Tree Dao. He's a very famous guy who created Flash Attention. I know he and his work at Princeton, they're working on a lot of algorithms to make things faster. He's with a company called Together AI. And there's a lot of work in the industry around making these things faster and more efficient. But today, you have to sort of bear with what we got. And sometimes you have to make some adjustments and clever ideas to sort of make your application work. But great question. Yeah, OK. I'll be here around. Thank you very much. And I want to call Laurie now from LlamaIndex to please come and do his presentation.
Thank you, Ofer. All right, let's see if I can set all of this stuff up. Sweet. All right, this is a great crowd. So first order of business is gotta take a speaker selfie. Everybody pretend you've had a great talk from me. Because I never remember to do it afterwards. All right, cool. So, hi everybody, I'm Laurie. I am VP of Developer Relations at LlamaIndex. Once upon a time, I was co-founder of NPM Inc., so some of you may remember me from when I used to talk incessantly about JavaScript. Now I talk incessantly about AI. The common thread is that I talk incessantly. Today, I'm going to be telling you about LlamaIndex. I'm going to tell you what it is, why you should use it, and what it can do for you, including retrieval augmented generation, world-class document parsing, structured data extraction, and of course, autonomous agents, which is what we're mostly talking about today. These slides have not been advancing. Come on. You'll catch up. Yeah, there we go. Fancy remote. Cool. So what is LlamaIndex? We are a bunch of things. To start at the most obvious, we are a framework in Python and TypeScript for building generative AI applications. But that is not all that we do. One of the most popular things that we do is a service called LlamaParse at cloud.llamaindex.ai. What it does is it parses complex document formats, so think PDFs, Word files, PowerPoints, stuff like that, into a format that is more easily understood and digested by LLMs. This turns out to be critical for LLM-based applications, turning information into something that they find easy to understand. LlamaParse is free to use for 1,000 pages a day, and it will demonstrably improve the accuracy of your application, so we definitely think it's worth a try. We also have a service called Llama Cloud, which is our enterprise service. If what you want to do is stuff a bunch of documents into one end and get a retrieval endpoint out of the other without having to bother about any of the stuff in between, then this is the service for you. You can think of it as LlamaIndex building a LlamaIndex application for you and hosting it and scaling it and all of that good stuff. Unlike the rest of LlamaIndex, it does cost money, but you know, it had the word enterprise, so you knew that already. And then there's Llama Hub, which is our registry of helper software. This is also free. If you need to connect to any database in the world, we've got you, so you can load your data from anywhere. If you need to get your data out of Notion or out of Slack or out of Google Drive or whatever, we have connectors that will do that. If you need to store your data in a vector store, and you do, then we support all of them, including Vectara, of course. We support over 30 different LLMs, so OpenAI, Mistral, Anthropic, every local LLM via Ollama. And if you want to build an agent, we have lots of pre-built agent strategies and lots of pre-built agent tools that you can download and incorporate into your software from Llama Hub. All of which is to say, why should you use LlamaIndex? Because we are going to help you go faster. All of this pre-built stuff is there to help you put together an application quickly and easily. Don't get stuck figuring out the basics. We have solved a bunch of the foundational problems for you, so you can focus on being novel and interesting and solving your actual business problems. So let's talk about what this framework can actually do for you. And one of the biggest things that we do is RAG, which stands for Retrieval Augmented Generation. Hands up if you feel like you know what RAG is. Okay, nearly everybody, so I'm going to skip through the bit where I explain what RAG is. But just for the handful of you who didn't raise your hands, it's fundamentally a response to a limitation of LLMs. You want to give your LLMs to be able to answer questions about your data. They don't have all of your data, so you have to give them your data. But to give them your data, you can't give them your data all at once because they have limited context windows. So instead, you have to be selective. That is the retrieval part. You have to find the most relevant context for your application and hand that to the LLM. That is essentially what RAG is doing, but I'm not going to go into details now because I've only got like 12 minutes, and you've probably heard it 1,000 times already. But the theory of RAG is different from the practice of RAG. There's a whole bunch of steps to it. You have to ingest your data. You have to parse it into chunks. You have to embed those chunks. You have to turn them into vectors so that you can use vector search to find them. You have to store them in a vector store. And then you use a query to perform semantic search on the chunks in your vector store. What you get out of your vector store is stuff that is in meaning semantically similar to your query. And you hope, and it mostly turns out to be true, that your question and your answer are semantically similar to each other. In LlamaIndex, doing all of that stuff that I just talked about is 5 lines of code. It's these 5 lines of code. This is what we mean by when we say we help you go faster. You can see us loading our data from the file system into documents. You can see us putting those documents into a vector store. The vector store does the embedding for you. Then we turn that index into a query engine, and we ask a query, and we get a response. But the point of LlamaIndex in general, and indeed the point of this talk, is that RAG by itself is not enough to do the things that you want a generative AI application to do. That's why I skimmed through the RAG section so quickly. RAG is limited. It tends to work for simple questions over small sets of documents, and there are a number of ways that RAG can fail. One task RAG is not great at is summarization. If you think about what RAG is doing, RAG is a search. It is looking for data that is semantically similar to your query. If you ask it for a summary of your document, it's going to search for a summary of your document, and your document does not usually contain a summary of itself. It's going to fetch chunks about things that it's not going to be able to answer a summarization question. If you ask it for a comparison question, it's going to try to simultaneously fetch chunks about the two sets of things that you're comparing. You're comparing A and B, it's going to get chunks about A and B, but it's not necessarily going to know which chunk is about A and which chunk is about B. So naive RAG can fail in comparison questions there. And in general, it fails at multi-part questions. When you have a complicated question, RAG tries to do it all in one shot, and it doesn't necessarily always get it. So that's why we say that RAG is extremely powerful. It is a magical technique, but it is not sufficient. It is necessary, but not sufficient. So how do we go beyond the limits of RAG to fully utilize the power of LLMs? There's two ways that you can go. One is to improve the quality of your data. That is why we built LlamaParse and put so much effort into it, because getting better data demonstrably helps your application improve at answering questions about it. And the second way is to make your querying more sophisticated. And that's the one I'm mostly going to be focusing on today, because the way that you're going to want to improve your querying strategy is by using agentic strategies. We've talked a bunch about agents already, so I'm not going to go deep into what they are. But what I mean when I say an agent is a piece of semi-autonomous software that uses tools to answer questions and achieve a goal. And the specific reason, the specific way that an agent is different from regular software, the software that came before, is that you don't necessarily know in advance what steps your agent is going to take to achieve that goal. You've just given it a goal and a set of tools, and you've told it, figure it out. And that is a radically wild new way to write software. So let's think of the ways that a RAG pipeline is limited. It's single shot, so just one question and one response. There's no query understanding. It's just semantic search against the text of the query. And there's no tool use, so you can't go back and get more information. And you can't modify the state of the world in response to your query. There's no reflection or error correction. If your RAG pipeline gets the wrong answer, it doesn't actually check whether it got the wrong answer. It just says, here you go, here is the answer that I got. And finally, there's no memory. Every question is brand new. It's never seen any of the previous questions before. It doesn't know the broader context in which you're asking your questions. We can fix all of those with agents. By building Agentic RAG, like I said, you can do a whole lot better on every one of those fronts. You can make your queries multi-turn, so you can have your agent understand the question and plan how to get to the answer in multiple steps. You can make RAG just one of many tools available to your agent, so that it can interface with the environment, get more information, get summaries, that kind of thing. And you can use reflection to figure out if your response is accurate. And course correct if not. That is one of the most useful things about an agent, is that instead of just getting a question and getting an answer, you can have an agent with an LLM that has a second LLM checking the results of the first one, going, does this thing look like it's hallucinated? Does this thing look like it actually answered the question? Does this question look like it is useful, or if it needs more context or anything like that? You can get your agent to your agent or your multi-agent system to answer questions that way. And of course, you can add memory, so that each step becomes part of the larger context towards the solution. Getting all of this stuff done is a lot of work, but that is why LlamaIndex as a framework exists. We have created built-ins that handle all of this stuff for you. These strategies that I'm talking about exist on a spectrum of complexity. You don't necessarily want to create the most complicated agent that you can possibly imagine. As we were talking about, one of the problems with agents is their performance. They can be very, very slow, especially if you give them lots and lots of steps. So you have to make trade-offs in terms of the size of the model you're using, how many LLM calls you're going to make, how many correction steps, how many self-reflection steps you're going to allow, that kind of stuff. You have to balance performance with latency and cost. And not all of these strategies are fully agentic by themselves. Some of them are just like ingredients that you would put into an agent to make something fully agentic. So let's very briefly break down each of these methods in turn. The first agentic strategy is routing. We talked about this, Ofer mentioned this earlier. This is the simplest form of agentic reasoning. Given a query and a set of tools, it will pick the tool that is the best tool to answer the question. So you could solve the summarization problem this way. So in addition to a RAG pipeline as a tool, you also give it a document summary as a tool. When it gets a question, it decides, am I looking at a question that can be answered by RAG, or am I looking at a question that can be answered by a summary, and it picks the correct tool that way. The next tool that we can add to build up an agent is memory. This is theoretically simple. You just give it the history of all of your previous questions and answers. As you get more complicated, as your history gets longer, that becomes more complex. You have to be able to condense your history down so that it fits into the context window. You might want to create a RAG pipeline that queries your history and fetches only the relevant bits of your history when you're making a query. We can also add one-shot query planning. One way that you do this is you'd get your LLM to take a complex question and break it into a series of smaller questions that a RAG pipeline would find easier to answer. You then get these 3 or 4 different answers from your RAG pipeline, and you get the LLM to do one more call to condense those answers into a single coherent answer to the more complicated question. And the way that we're making all of this happen is through the most important part of agentic strategies, which is tool use. It is an amazing sort of side effect of the fancy autocomplete that LLMs are, is that they can fancy autocomplete the JSON structures necessary to call an arbitrary Python function. I don't think anyone was expecting it to be able to do that. That's a really surprising side effect of creating autocomplete, but it's great because it means that they can call arbitrary functions and do arbitrary tasks. So when you use tool use, your query gets modified from being a query to a specific call to the tool. So in text to SQL, which we were looking at earlier, your query gets turned from natural language into SQL. If it's an API call, it gets turned into, like instead of a question that says, what's on my calendar today, you get an API call to your calendar API saying, fetch the last 10 events. Tool use, it's a duplicate slide. There we go. So all of those things, routing, memory, tool use, that kind of stuff, they are the basic agentic strategies, but they are just the minimum necessary to create an agent. To create a fully agentic system, we need to go further. We need to make it multi-turn. We need to give it reasoning and planning. We need to give it reflection, which I talked about. And let's talk about very quickly how we get those things done. There's 3 types of agentic reasoning that I want to talk about today. One of them we've already seen, and that is sequential. In this one, which is often called the react pattern, reasoning plus action, also known as chain of thought, your agent generates this distinctive pattern of making an observation about the world, deciding what it should do to get closer to its goal, and then taking action based on the tools that it has available to it. In React, it stays in a loop, trying to get closer and closer to its goal with every step until it either gets there or it gives up. It's very simple, it's very basic, it doesn't always work. The next level of sophistication in terms of agent reasoning is DAG-based reasoning. In this, it creates a directed acyclic graph, which you can think of as like a flowchart, a series of steps from your goal to your end, from your starting point to your goal, and all of the steps and all of the dependencies between those steps. It will come up with this list of steps that it thinks it should take, and execute them one after the other. A critical part of that planning process is the ability to replan when things don't work out. Your agent can observe the state of the world and see if the plan is going according to plan. If it's not, it can say, okay, the state of the world is not what I was expecting it to be after 3 steps into this plan. Let me create a new plan and try and get to the goal from there. You can also, of course, get a human in the loop to tell the agent whether it's getting there. But still, DAG-based planning is best when the task is simple enough that an LLM can try and figure out a plan all the way from 0 to the goal in one shot. That is not always going to be the case, especially when the task is open-ended or particularly complex. And in that case, you would reach for the final strategy, which is tree-based search. In this one, you can imagine an LLM basically making experiments. It looks at the current state of the world and it comes up with a handful of different things that it could do. And then it imagines what the world would be like after it did each of those things, and then for each of those things, it repeats the process. Let me think of 3 more things that I could do that would get me closer to my goal. After a couple iterations of that, it looks at the leaves of this tree that it's generated and says, which of these leaves is closest to the final goal that I was attempting to reach? And then it trims the tree. It says, okay, everything except that one leaf is going to be discarded, and I'm going to follow those steps and see where I get. And then if it's at its goal, then it's done. And if it's not, it generates a new tree starting at that leaf. One of the things that you have to balance when you're thinking of language agent tree search or tree search in general is balancing exploration versus exploitation. Exploration is like how many branches it's going to create at each time, and exploitation is how far down the tree it's going to go before it decides that it needs to trim the tree. And that is all I've got time for today. Usually I would be talking about workflows, I would be talking about Llama deploy, I'd be talking about all of the things that we do to make it easy to deploy stuff and create complex multi-agentic systems, but I'm already over time. So thank you all for your time and attention, and it was great talking to you. I can take one question. I feel like I'm already overstaying my welcome. Yeah.
So when we talk about the query breakdown by the agent, so in case of customizing it to different domains, is there a way to fine-tune that query breakdown for domain-specific data or queries?
Sorry, could you repeat the question?
So with the agents, we see that based on the type of query, it can decide what actions to take, like whether to, for example, with the summarization query, so it fetch the available data first and then run a summarization of that. So for more nuanced breakdowns, which are dependent on your domain-specific data, is there a way to fine-tune this query breakdown or query transformation?
So the question is, if you have a particularly complicated set of data and you need to break down your query from natural language to one of a very specific set of techniques to answer that question, how do you do that? The answer, you mentioned fine-tuning. Fine-tuning is one of the ways that you can do that. You can create a small specific model that has been trained to answer questions based on that. You can also just use regular prompt engineering. You can say, I am expecting a series of questions that are going to fall into these 3 categories. If you see this kind of category, this is the tool you should use, and these are the techniques that you should use when you're answering that tool. Does that answer your question? All right, and we're all done. Thank you.
Thank you, everybody. Thank you, Lori. Give it up one more time for all of your speakers. And one more time for our host, GitHub. We have the space for another hour and a half or so, so feel free to hang out. We've got drinks in the back. We'll be here. Come grab any of the speakers if you have questions or anybody else. Thank you all again for all of your attention.